Now that we've seen how regularization can play a role in the classification setting, let's observe in our toy data set what happens to decision boundaries as we introduce a regularization penalty. We're going to work with that degree 20 features. So fitting logistic regression model with features of polynomial degrees 20, which led us to this technical term that I call the crazy decision boundary. And the parameters had very large magnitude. In fact, they varied from minus 3,170 to 3,803. So they were very big. Now we're going to take the same setting, same number of features, same data, same everything, but just vary the parameter lambda and see what happens. And here we're showing the results of doing exactly that. When lambda is equal to 0, we get very large coefficients, while when lambda is large, like 10, we get, good size coefficients, let's say smaller coefficients. Okay, and so for lambda equals to 0, we had that crazy decision boundary, and for large lambdas, we have a nicer, smoother boundary. In fact, I trust the decision boundary with lambda equals 10 much more than I trust the one with lambda equals 0. And that decision boundary with lambda equals 10 looks a lot like that really beautiful one I got with the parabola and fit my data really well. But here I added tons of more features, but nonetheless adding a little bit of regularization help us get that really nice separating plane that I can trust. We can also look at the coefficient paths, what happens to our coefficients as we increase the penalty lambda. So in the beginning, when we have an unregularized problem, these coefficients tend to be large, but as we increase lambda, they tend to become smaller and go to 0. I've used the review data set, product review data set here, and I picked a few words and fit a logistic regression model just using those words with different levels of regularization. So for example, the words that have positive coefficient tend to be associated with positive aspects of reviews, while the ones with negative coefficients tend to be associated with negative aspects of reviews. What is the word in quotes that has most positive weight? Well, if you look at the key here, you see the word that has most positive weight is actually an emoticon, smiley face. Well, the word that has most negative weight is another emoticon, which is a frowny face. And in the beginning, all of these words have pretty large coefficients, except for the words here near 0, which are words like this and review, which are not associated with either positive things or negative things, although if the word review shows up, it's slightly correlated with a negative review. But in general, these coefficients are much smaller than the others. And as I increase the regularization lambda, you see the coefficients tend to become smaller and smaller. And if I were to keep drawing this, they'll eventually go to 0. And now, if I were to use cross-validation to pick the best lambda, I'll get a result kind of around here. And I'm going to call that lambda star. And so that's what you do, you use cross-validation to find that point where it's fitting data pretty well, but it's not overfitting it too much. And as a last point, I'm going to show you something that is pretty exciting, is really beautiful about regularization logistic regression. Regularization doesn't only address the crazy, wiggly decision boundaries, but address some of those overconfidence problems that we saw with overfitting regularization. So I'm taking the same coefficients, same thing that I've learned, the lambda is increasing, the range of coefficients decreasing, they're getting smaller, but I'm plotting in the bottom here the actual decision boundaries that we learn and the notions of uncertainty on our data. So if lambda is equal to 0, we have this highly overconfident predictions. if lambda is say 1, not only do I get a more natural, the kind of parabola-like decision boundary, even though I'm using degree 20 features, polynomials with degree 20 is features, I get a very natural uncertainty region. So the region where I don't know if it's positive or negative is really those points in the boundary, which are kind of between those clusters of positive points and the clusters of negative points. And you get this kind of beautiful, smooth transition. So by introducing regularization, we've now addressed those two fundamental problems where overfitting comes in with logistic regression.